Okay, we're going to pick up in chapter 13. This will be part 3, and we ended part 2 talking about erosional features of valley glaciers. So we'll start part 3 with erosional landforms and features of continental glaciers. One major difference between a valley glacier and a continental glacier is the areas that have been eroded by continental glaciers are often smooth and rounded. Picture on the right shows one of our features, and that's an ice-scoured plain. So that's going to be a large area where your continental glacier removed soil and sediment. Typically in these areas you might see some deranged drainage that we've talked about. You also see lakes and swamps in areas of low relief, as you can see demonstrated by this picture of an ice-scoured plain. Now, we have a term called glacial drift, and glacial drift is all the sediment that is deposited by glaciers. It covers vast areas of the northern U.S. The picture on this slide is of a glacial erratic. So that is a rock fragment that's carried from the source by a glacier. The reason we say it's an erratic is because it was obviously not derived from the underlying bedrock. So the erratic that you see here was carried a significant distance. Now there's two types of drift. We have till, which is all the sediment that's deposited by glacial ice. So you can see in picture A, all of this was deposited by glacial ice. Till can be found deposited in moraines, which we'll talk about in a minute, and as well as elongated hills known as drumlins, which you can see in picture C. These elongated hills that I'm circling are the drumlins. In addition to till, the other type of glacial drift is a stratified drift that you can see in picture B, and notice you can see the different layering. So stratified drift is going to be in those layers, and it's also going to show some degree of sorting. Now let's talk a little bit about the different types of moraines we can have. So an end moraine is till that's going to be deposited at the terminus of a glacier that's been stationary for a few years, maybe even decades. So the flow is still going to continue in the stationary glacier, so you're going to get that continued sediment deposited at the terminus. So in this picture, your terminus would be right here. So all this sediment is being deposited by that stationary glacier. You can also have what's known as ground moraine. That is your sediment that's released from the melting glacier as your terminus starts to retreat. You could have what's known as a recessional moraine, which is an end moraine that's formed when the glacier's terminus retreats and then stabilizes. So anytime your terminus retreats, you can have a recessional moraine formed. And you can see in this picture, the lines are pointing to a recessional moraine, a ground moraine, as well as the terminal moraine. You could also have what's known as a lateral moraine, and that is a ridge of sediment that's deposited along the margins of your valley glacier. So your lateral moraine are going to be on the edges, like this. The medial moraine is a moraine that's carried on the central surface of your glacier, and it forms when two lateral moraines merge. So you can see right here is our medial moraine. So we had a lateral moraine coming down this way, we had a lateral moraine coming down this way, and they merge into that medial moraine. And then we could even have valley trains, which are long deposits, narrow deposits of stratified drift from braided meltwater streams. If we look at some pictures, this shows a good picture of your lateral moraine. You can see it pointed out. And then you see the medial moraine where your lateral moraines are going to join. Some other landforms that are composed of stratified drift. You could have what's known as a kettle. A kettle is a depression that's formed from a retreating glacier that leaves a large block of ice that is going to eventually melt. So basically it's going to be a depression, and it's a depression because you have this heavy block of ice sitting there that eventually melts. Drumlins, we mentioned, are our elliptical hills of till. A lot of times you will see fields of drumlins, and you can see them pointed out in this bottom picture. And then we have our outwash plain. So your outwash plain is all the sediment that's deposited by the meltwater from your glacial terminus. So all this area in here that I'm putting this little dash by would be your outwash plain. You might have what's known as kames. Those are going to be your conical hills of stratified drift. They were originally deposited in a depression or on a glacial surface. So here's some of our kames right here. Circle them for you. And then again we have our eskers. An esker is a long sinuous ridge of stratified drift. Remember, sinuous means bending. So it's this bending ridge of stratified drift. It is deposited by running water in a tunnel beneath ice that's not going to move. So just to point out some other features that you can see in here, notice this is our terminal moraine. So our glaciers retreated, so we then also have our recessional moraine right there. Here's a picture of our esker right in here. This is a good picture showing you the valley trains as well as the kames. So here's our kames of our depression where our ice, and then this area would show your valley train. Now in your glacial lakes, you also see some deposition, and you could see what's known as varbs. So all this area right in here is considered to be a varb, which is your finely laminated mud deposit, and you can see the laminations. This right here would be known, that I'm circling, as a drop stone. It is a piece of gravel in a lake sediment. So it's basically carried by your glacier and then being deposited. One important thing I want to mention is what's known as Milankovitch theory. The Milankovitch theory explains that cyclic variations in the Earth's climate as a result of variations in the Earth's rotation and orbit. So it's going to alter the amount of solar radiation that we receive. So Milankovitch basically said that was a cause of our glacial episodes. And he pointed out 3 aspects of the Earth's orbit that could cause the glacial episodes. The orbital eccentricity, which is the amount of change in the Earth's orbit around the sun. The axial tilt, which is a shift of the angle between the Earth's axis and the line perpendicular to the Earth's orbital plane. And the precession of our equinoxes, which is a change in the time of the equinox. And these are illustrated in pictures A, B, and C. So keep in mind, he came up with this idea in the 1920s. It was initially ignored, and it came about to be more widely thought of and regarded in the 70s when it was actually accepted. We do have some short-term climatic effects. We're not sure what causes them, but this slide talks about several of the hypotheses. So short term could be caused by variations in our solar energy. So basically a change in that energy output from the sun. And anytime our solar system would go through a region of dust. Another short-term event could be caused by volcanism. Ash and gas can reflect that solar radiation and basically cause a cooling. Also, that large-scale events. If you remember, we talked about Mount Tambora, which was the year without a summer because it blocked that solar radiation. We're not sure what short-term events actually caused our little ice age. Okay, this ends chapter 13.